we have two real Revit files. In the requirements folder, 8 different files. This is how requirements are typically shared between project teams. The prompt says, take all BIM models, convert them to Excel, check each project against its requirements. The AI agent starts working. It scans the folder structure, locates the models, Revit Advanced, 2 dashboards side by side. Here are the results. The summary dashboard. Requirements are 3 columns and verification is 1 prompt. In this video, you'll see how a single AI-powered query can replace hours of manual CAD BIM model verification. I'll show you how AI agents can analyze requirements in any format, verify any CAD BIM models, and provide a detailed report without the need for a zoo of programs and plugins. Let's open VS Code and connect this folder as our workspace. Now let's open our project folder inside the code editor. We simply copy the path and paste it in. Next, we launch an AI coding agent, such as Claude Code, Google Joules, or OpenAI Codex, to fully automate the data processing pipeline. Inside the Revit project, under the model folder, we have 2 real Revit files. In the requirements folder, 8 different files, the same 20 validation rules written in 8 completely different formats. Here is the execution plan, a Word document. Entity, attribute, constraint, severity, category. This is how requirements are typically shared between project teams. Next to it, an Excel matrix. The same rules, but in a different layout. Element types as rows, attributes as columns, constraints at the intersections. 1 set of rules, 2 very different representations. And this is just the beginning. Here is the Solibri model checker format, a JSON file with its own structure. Rule templates, component filters, operators. Every single rule takes dozens of lines of code. Beyond Solibri, we also have CSV, a nested JSON, DWS for AutoCAD standards checking, and IDS from Building Smart. Each verification tool demands its own format. Let's switch to the IFC project. 2 model files, and in the requirements folder, another 8 files. Same story, different formats, same rules. 16 rules, 250 lines of XML. So here's the problem. 15 requirement files, 8 different formats. Each with its own structure, its own syntax, its own way of expressing the exact same rules. This is the complexity we are about to eliminate. Back to Claude Code. Clean chat. The verification folder is open. We type 1 prompt. The prompt says, take all BIM models, convert them to Excel using data-driven construction converters from GitHub. Check each project against its requirements, even though they come in different formats. Create dashboards based on the example. The AI agent starts working. It scans the folder structure, locates the models, finds the data-driven construction converters on GitHub, and begins the conversion pipeline. Both IFC files are converted. The Revit models follow. In parallel, the agent writes parsers for every requirement format. The agent builds a unified validation engine, runs every model against every requirement format, and generates the dashboards. 33 dashboards, 1 for each combination of project and requirement format. Let's see the results. Revit Advanced, 2 dashboards side by side, left validated against JSON, right against Solibri, both show 76.3%, 199.31 passed, 599 failed, identical. This is the key insight. It does not matter which format the requirements are written in. If the rules are the same, the result is the same, the format is unnecessary complexity. No matter what software or data format your company uses, at the core, you're always working with the same thing. A CAD database, tables that store element parameters and their values. To validate and apply the data in your case study, you only need 3 columns: the group or type name, the parameter name, and the boundary conditions for its values. The core idea: we type a second prompt. Read all requirement files across all formats. Create a single rules file with all unique rules. It extracts every rule, removes duplicates, and consolidates them into a single list. Result: 16 unique IFC rules, 20 unique Revit rules. All rules are correct and found across all 7 source formats. Let's open the DDC files. Here they are, side by side, IFC rules, Revit rules. 3 columns in bold, entity, attribute, constraint. This is the essence of every rule. Visually, you immediately understand what matters. 3 columns, instead of 15 files in 8 formats, 2 simple Excel spreadsheets, 6 kilobytes each. The final step, third prompt, check all projects against these DDC requirements and generate a clear dashboard along with a PDF report. The agent takes our 2 simple DDC files, reads the converted model data, and runs every element through every rule, counting pass and fail for each. Here are the results. The summary dashboard. 70.7% overall compliance. 3,235 checks passed. 1,343 failed. 4,578 total. 36 rules across 4 projects. And next to it, the PDF report, DDC validation report, 79 pages, key findings, worst and best performing rules, detailed breakdowns for every project, every rule, every failed element. 3 prompts, 4 models, 36 rules, nearly 5,000 checks, a dashboard and a full PDF report. And at the core of it all, 3 columns. Entity, what we check. Attribute, which parameter. Constraint, what rule it must follow. That is data-driven construction. A model is data, requirements are 3 columns, and verification is 1 prompt. Every project in the architecture, engineering, and construction sector involves dozens of systems: ERP, 4D, 5D, CAD BIM, supplier systems, and construction site software, each of which generates its own data and has its own requirements. The result? Hundreds of requirements across different disciplines and in various formats. But each one, regardless of its source, boils down to 3 components: an entity, an attribute, and a constraint. Technical specifications in PDF format, IFC models, Excel spreadsheets, CAD drawings, all of this is normalized into a single schema. Open data, open source code, AI agents that verify requirements at any scale. Learn more about requirements gathering methods and the verification process in the book Data-Driven Construction.